It's understandable that project teams may have concerns uploading their smart contract code to a SaaS service like Mythex. So Mythex provides a privacy guarantee for the smart contract code submitted using their SaaS APIs. First one is that the code analysis requests are encrypted with TLS. And to provide comprehensive reports and improve performance, the Mythex service stores some of the contract data in its database, including parts of the source code and bytecode. But that data never leaves their secure server and is not shared with any outside parties. It keeps the results of the analysis, it retains them so that it can be retrieved later, but the reports can be accessed only by the project team, and the service enforces authorized access to such results. Performance is usually a concern with security tools that perform deep analysis, such as with symbolic checking or fuzzing, because they may require a lot of compute resources and proportionately longer amounts of time for iterating through their analysis to get good coverage and precision. So in this case, Mythex can be configured for 3 types of scans depending on the time expectation. Quick scans run for 5 minutes, standard scans run for 30 minutes, while deep scans run for 90 minutes. And as you can imagine, standard scan gives better results than quick scans, and deep scans better than standard ones. So one can customize this, the type of scans, according to the development phase and time available. So for example, quick scans can be perhaps run by developers during their code commits, and standard scans can be run at certain project milestones, while deep scans that take a much longer time can be run on the nightly builds when you have more time. Mythex comes in different versions so that it can be accessed via multiple ways. There is a command line interface version that provides a unified tool access to Mythex. There is Mythex.js, which is a library to integrate Mythex in JavaScript or TypeScript projects. There is a Python library, Mythex, to integrate Mythex in Python projects. And finally, there is a Visual Studio Code extension for Mythex that allows a project to scan smart contracts and view the results directly from the code editor. As for pricing, Mythex has 4 pricing plans. The first one is an on-demand pricing plan that costs $9.99 for 3 scans. And all 3 scan modes, quick, standard and deep, are available as part of this plan. The second pricing plan is a developer plan that costs $49 a month. This gives access to quick and standard scan modes only, and it allows 500 scans a month. The third one is a professional plan which costs $249 a month and gives access to all scan modes and 10,000 scans a month. And finally, there is an enterprise pricing plan that allows for custom pricing, where custom plans can be decided between a project team and consensus diligence that meets the team's specific needs. Let's now move on to another tool from consensus diligence called Scribble. Scribble is a verification language and a runtime verification tool that translates high-level specifications into Solidity code. It allows one to annotate a Solidity smart contract with specific properties. There are 4 principles or goals with Scribble. 1. that specification should be easy to understand by developers and smart contract security auditors. 2. Specification should be simple to reason about. 3. Specification should be efficiently checked using off-the-shelf analysis tools. And 4. A small number of core specification constructs should be sufficient to express and reason about more advanced constructs. So Scribble transforms annotations made within smart contract code using its specification language into concrete assertions. And then with those instrumented contracts that are equivalent to the original ones, one can use other tools from consensus diligence such as Mithril, Harvey, Mythex to leverage these assertions for performing deeper checks. So Scribble is a relatively newer tool from consensus diligence and sounds very powerful in its capabilities. So I would strongly encourage everyone to take a look at the documentation of Scribble, take a look at the motivations and the underlying concepts driving this tool, and also test it out to explore all its capabilities. Fuzzing as a service is a service that has been recently launched by Consensus Diligence, where projects can submit their smart contracts along with embedded inline specifications or properties written using the Scribble language that we just talked about. These contracts are run through the Harvey fuzzer, which uses the specified properties to optimize fuzzing campaigns. And any violations from such fuzzing are reported back from the service for the project to fix. Carl is another security tool from Consensus Diligence, and this can be used to monitor the Ethereum blockchain for newly deployed smart contracts that may be vulnerable, and this can be done in real time. Carl checks for security vulnerabilities using the Mithril detection engine, also from Consensus Diligence, and this can be an interesting monitoring tool for detecting vulnerable deployed smart contracts, but not really during security auditing or reviews for projects that are yet to be launched. Another security tool from Consensus Diligence that is not specifically meant for auditing but interesting nevertheless is Theo. Theo is an exploitation tool with a Metasploit-like interface and provides a Python REPL console from where one can access a long list of interesting features such as automatic smart contract scanning, which generates a list of possible exploits, sending transactions to exploit a smart contract, transaction pool monitoring, front-running, back-running transactions, and many others. A tool that could be very handy in the manual analysis phase of smart contract auditing is the Visual Auditor. This is a Visual Studio extension, again from Consensus Diligence, that provides security-aware syntax and semantic highlighting for Solidity and Viper languages. Examples of things that are highlighted include modifiers, visibility specifiers, security relevant built-ins such as the globals, transaction origin, message data, and so on. Storage access modifiers indicating if it is in memory or storage. Developer notes in comments such as to-dos, fix-me's, hack, etc. Event invocations, operations, constructor fallback functions, state variables. It has support for review-specific features such as audit annotations and bookmarks, exploring dependencies, inheritance, function signature hashes. It supports graph and reporting features such as interactive call graphs with call flow highlighting, UML diagrams, and access to Surya features, which we'll talk about in the next slide. It also supports code augmentation features where additional information is displayed when hovering over Ethereum account addresses that allow one to download the bytecode or source code or open it in the browser, hovering over assembly instructions to show their signatures, and hovering over state variables to show their declaration information. So overall, the visual auditor is almost a must-have tool while manually reviewing Solidity or Viper code during audits. Surya is a visualization tool from Consensus Diligence that helps auditors in understanding and visualizing Solidity smart contracts by providing information about their structure and generating call graphs and inheritance graphs that can be very useful. It also supports querying the function call graph in many ways to help during the manual inspection of contracts, and this is integrated with the visual auditor tool that we discussed in the previous slide. Surya supports several commands such as graph, function trace, flatten, inheritance, dependencies, parse, generating a report in the markdown format, etc. It is always helpful to have a registry of unique vulnerabilities so that everyone can refer to a single source, keep it updated, and use them in interesting ways. One such effort is the Smart Contract Weakness Classification Registry, or SWC registry. This is an implementation of the weakness classification scheme proposed in EIP 1470. It is loosely aligned to the terminologies and structure used in the Common Weakness Enumeration CWE from Web 2 while being specific to smart contracts. The goals of this project are threefold. First one is to provide a way to classify security issues in smart contract systems. And the second one is to define a common language for describing security issues in smart contract systems architecture, design, or code. And finally, serve as a way to train and improve smart contract security analysis tools. This repository is currently maintained by Consensus Diligence and contains 36 entries as of now. Securify is a security scanner developed by Chain Security. It's a static analysis tool for Ethereum smart contracts. It's written in Datalog and supports 38 plus vulnerabilities. We won't go into the details of this tool over here, but I would encourage you to look it up. Verx is a formal verification tool, again from the Chain Security team, that can automatically prove temporal safety properties of Ethereum smart contracts. The verifier is based on a combination of three ideas. One, reduction of temporal safety verification to reachability checking. Two, a symbolic execution engine used to compute precise symbolic states within a transaction. And three, the concept of delayed abstraction, which approximates symbolic states at the end of transactions into abstract states. The details of this tool or the concepts behind it are out of scope over here, but I would encourage you to look at their website for documentation and their academic paper for greater details behind the theory of this tool. Smart Check is a security tool from Smart Tech. It is another static analysis tool for discovering vulnerabilities and other code issues in Ethereum smart contracts written in Solidity. An interesting implementation aspect here is that it translates Solidity source code into an XML based intermediate representation and then checks it against XPath patterns. For context, XPath stands for XML path language, which uses a path notation for navigating through the hierarchical structure of an XML document. K framework is a verification framework from the runtime verification team. It includes KEVM, which is a model of EVM in the K framework. It is the first executable specification of the EVM that completely passes the official EVM test suites, and so could serve as a platform for building a wide range of formal analysis tools for EVM. Again, we won't go into any level of details for this framework here because we really can't do much justice to such deep frameworks in one slide or a few minutes. But I would strongly encourage you to look at the documentation to get a better understanding of its capabilities. Certora Prover is a formal verification tool from Certora. It checks that a smart contract satisfies a set of rules written in a language called specify. Each rule is checked on all possible transactions, not by explicitly enumerating them, of course, but rather through symbolic techniques. The prover provides complete path coverage for a set of safety rules provided by the user. For example, a rule might want to check that a bounded number of tokens can be minted in an ERC20 contract. The prover either guarantees that such a rule holds on all paths and all inputs, or produces a test input known as a counterexample that demonstrates a violation of this rule. And this problem addressed by Certora Prover is known to be undecidable, which means that there will always be some pathological programs or rules for which the prover will time out without a definitive answer. This prover takes as input the smart contract, either the bytecode or the Solidity source code, along with a set of rules written in the Certora's specification language specify. The prover then automatically determines whether or not the contract satisfies all the rules provided using a combination of two fundamental computer science techniques known as abstract interpretation and constraint solving. I would encourage everyone to take a look at their website and documentation to understand how the prover tool works and the technology behind it. DAppHub's HEVM is an implementation of the EVM made specifically for unit testing and debugging smart contracts. It can help run unit tests, property tests, and also help interactively debug contracts while showing the Solidity source code, or also run arbitrary EVM code. So with this, we have touched upon the various security tools that you may come across in this space. There are likely others that we haven't covered here, purely for constraints of time and scope, and some like SMT Checker, which we have covered in the Solidity module earlier. For all these tools, the best way to understand their capabilities and specific use cases is to really install and experiment with them. And I would really encourage everyone to do that with some of these tools at least. Let's now talk about a related concept called Capture the Flag, or CTF as it is popularly known as. CTFs are fun and educational challenges where participants have to hack different dummy smart contracts that have vulnerabilities in them. They help understand the complexities around how such vulnerabilities may be exploited in the wild. And the popular CTFs in the space of Ethereum smart contracts include Capture the Ether, which is a set of 20 challenges created by Steve Marks, which test knowledge of Ethereum concepts of contracts, accounts, and math, among other things. Then there is Ethernaut, which is a Web3 or Solidity based war game from OpenZeppelin that is played in the Ethereum virtual machine. And each level is a smart contract that needs to be hacked. The game is completely open source and all levels are contributions made by players themselves. Then we have Damn Vulnerable DeFi, which is a set of 8 DeFi related challenges created by Tinko, security researcher from OpenZeppelin. Depending on the challenge, one should either stop the system from working, steal as much funds as they can, or do some other unexpected things. And finally, we have the Paradigm CTF, which was a set of 17 challenges created by Samson at Paradigm. So CTFs can be a fun way to practically test out some of the things that you've learned in these modules. So I would encourage you to take a look at some of these and see how well you do in them. In summary, smart contract security tools are useful in assisting auditors while reviewing smart contracts. They automate many of the tasks that can be codified into rules with different levels of coverage, correctness, and precision. These tools are fast, cheap, scalable, and deterministic compared to manual analysis. However, they are also susceptible to false positives. They are therefore especially well suited currently to detect common security pitfalls and best practices at the Solidity and EVM levels. And with varying degrees of manual assistance, they can also be programmed to check for application level business logic constraints. Let's now talk about the audit process. This is critical to understanding the different stages in the life cycle of an audit from an auditor's perspective. It helps us understand what the auditors do at those different stages. How do they focus their efforts at those different stages? How do they interact with each other? How do they interact with the project team? And what the deliverables are at different stages of this audit lifecycle. And this process is going to be very different for every audit firm and very different even perhaps for different audits. Generalizing them, an audit process can be thought of as a 10-step process as follows. The first step is typically to read the specification and documentation of the project to understand the requirements, design, and architecture behind all the different aspects of the project. Then run fast automated tools such as linters or static analyzers to investigate some of the common security pitfalls or missing smart contract best practices that we have discussed. The third step could be to manually analyze the code to understand the business logic aspects and detect vulnerabilities in it. This could be followed by running slower but more deeper automated tools such as the symbolic checkers, fuzzers, or formal verification tools, some of which we have discussed in this module. And these typically require formulation of the properties or constraints beforehand, hand-holding during the analysis, and even some post-processing of the results. These stages may involve auditors discussing with other auditors the findings from all these above tools or even the manual analysis to identify any false positives or missing analysis. The auditors may also convey the status to the project team for clarifying any questions on the business logic or the threat model or other aspects. And all these aspects may be iterated as many times as possible within the duration of the audit so as to leave some time at the end for writing the report. And writing the report itself involves summarizing all these above details on the findings and recommendations. And finally, the audit team delivers that report to the project team, and then they discuss the findings, the severities, and the potential fixes that are possible. And there's also a step here where the audit team evaluates fixes from the project team for any of the findings reported, and then they verify that those fixes indeed remove the vulnerabilities identified in those findings. So this is how a typical audit process may look like and the different stages in its life cycle. Let's now dive in to discuss some details about each of these 10 steps.